last presentation for tonight.
All pages will stay this long, including our presentations. So let's start with number 8. It's called nailing. Alright, the statement first. Nail guns are often used to drive nail into wood. Build your own nail gun using liquid nitrogen evaporation. What is the maximum thickness of the woodwork that can be pierced by a nail fired with such a pistol if it should consume no more than 50 milliliters of liquid nitrogen per shot? Alright, so yeah, go engineering. but the important fact about this one is just that you have air stream or liquid nitrogen stream, and this is transferring its momentum on a bolt, and this is driving the nail into the wood. That's the most important thing about that. So how does it look like? We're going to construct the liquid nitrogen gun. We did it in his garden. And what you can see is that we use a typical gas bottle with hoses and valves and switches and put projectiles in it, and we're ejecting that with this switch you can see right there on the right side. Alright, so let's come to an experiment. This problem is all about momentum, so you have to be able to measure all your data, which means we have to construct a light barrier on our own. So we used an oscilloscope laser pointer, you should know how it works I think, different projectiles, and we're trying to measure which projectile is the best for our approach. So actually it's the biggest one, as you can see right there. It gave us the highest momentum. This is actually a funny curve. We said, okay, let's not take 50, but 210 milliliters of liquid nitrogen, and we filled our bottle and pressed the button as long as there was nothing more into it. So what you see is that there is a little plateau in the start, and then it decreases. This will be important in the end. So, the most important part is no animals were hurt by conducting our experiments.
That's our message.
Yeah, that's our message. Okay, now the hard part is the real part, but it will be fun in the end, I promise. Alright, let's go with the starting parameters. We have to use 50 milliliters of liquid nitrogen. This is actually equivalent to an amount of substance of 1.4 for 1 moles. So what do? You have your empty bottle, you open the valve, give in your liquid nitrogen, and then rapidly close it, so that the evaporation can create pressure. Very important is that for our ambient conditions, inside the bottle, your liquid nitrogen will become supercritical, which means that as the phase diagram tells you, we will pass this point because our temperature is actually 300 Kelvin, and therefore you have to know that the pressure is equal to the critical pressure of 34 bars. Nothing more can be measured, and that's experimentally proved. Alright, furthermore, as we go supercritical, there is no such value for the molar enthalpy of evaporation, so all the energy is transmitted into the bolt. That's important for our theory. As we can see right here, the main assumptions use an ideal gas equation, and we used the description of an adiabatic expansion for the shot process. Alright, so what's our answers? We use the typical approach that the mass times the acceleration is force, and this is equal to pressure times area. This long equation, we introduce the heaviside function because you all have seen the plateau form. In the start, there's critical pressure, but afterwards, as you go for the critical distance in your tube, the pressure will fall down, and then the second part of the formula will be applied. There's also an expression for the pressure of air, that's dynamic, but the problem asked us for the best solution, so we just assumed a simplification. And the simplification is that we have an adiabatic expansion of nitrogen against the vacuum. So the formula becomes easier and easier to calculate, which will be done in the next slide. If you just do the calculus, you get your values you desired, and it's actually for our biggest projectile against the vacuum, you will have 257.6 meters per second. That's very fast, actually. So it's really dangerous.
So don't point it at the audience.
Yeah.
Come on! What
Some stories about it. Alright. What you will learn from the equation right there, there's a dependence on the length of the barrel, as you see on the left side, which means that you have to prolong your length and the length of your barrel to get better values. But after certain time, this increase will not be such significant anymore. And the same applies for the initial value. We used actually 0.6 liters, but the smaller you go, the more pressure you will have for your system. So you should go as small as you can. Alright, we got momentum. Now the question is, how can you calculate the penetration inside the wood part? That's the main part of the problem. So we used the same empirical approach. What we did is we used the design to wood model, because wood is a natural material and every piece of wood is unique. That's very important to know. What parameters, type of wood, impact direction, and moisture content. And what we said is that it is actually a linear dependency. And this is what we want to prove for our project. So there was a second experiment. Yeah, we're actually night owls, as you can see. Still at 2 a.m. in the garden. What you do is you use a sand-filled impact tube and put it inside in a guiding tube. And what you do is you just put a nail with a little board under it, right here in this position. You measure the height above the nail, and then you just let the pipe do its thing and hammer the nail into the wood, which can be seen right here. And the very important thing is that perpendicular to the grain, you get worse results than hammering it parallel with the grain. So this is important to know. Alright, and this is actually our work. We use different kinds of nails, different kinds of woods, different kinds of impact directions. And what we see that the approximation of linearity is actually okay. Not all the points are on the scale, but most of them. And you will see that each wood type has a different kind of curve. But this is okay. We now make a case study for our best approach. This was actually a nail with 2.5 centimeters diameter and 5.5 centimeters length. Alright, what you do is you get all the results from your pipe experiments, and you want to make a prediction. How far can your nail go down or go inside the board? And that's what we did. And this is our prediction model. You insert the slope and the fitting parameter for each wood type. And what we predict is about 1.88 centimeters penetration depth. So is that okay or is it not? So we use our gun, and for a few nails it was correct, but for the mean value it was a bit off. So we have to remember that wood, a model has to be refined. You need more nails for the calibration, more wood samples for calibration, and you have to know that the prediction model will always be statistical, and the prediction of the physical parameters of wood is barely possible because every piece is unique. Alright, so the best value we achieved experimentally was 2.65 centimeters, and the upper limit in vacuum would be 3.7. Okay, this is the physical conclusion, but we will have a more important conclusion. And now that's where the fun part begins, because now there comes the insider, because a few people called us the shower team, and all the teams who were not there the last year will not know why. Because we were doing experiments inside the shower, and now it is in the garden. So you could call us actually the garden team. But to all of you, there's a very important message. Yeah, it improves your physics, but it improves